All right, decided to do this after looking through. I'm going to go ahead and post a video review for the Chapter 9 or Unit 9 homework. That way you can go through, make sure your answers are correct. If you've been having trouble on some of them, I think most people have had time to work through this one. But I wanted to just go ahead and give you some confirmation so that you can kind of check and see what's going on with these things. All right, so I'm going to do question by question, go through this quickly. Hopefully the video will be under 15 minutes. All right, so first question, red light has a frequency, red light has a blank frequency and a blank wavelength than ultraviolet rays. First off, your questions may not exactly match these, so just be kind of paying attention to what I'm doing as I'm answering these. Excuse me. All right, so looking at these, you have the chart right here, and it's going from radio waves to gamma rays. What we know is that you have 10 to the 2 meters here, 10 to the negative 2 meters here. So what that means is that wavelength, as we move from left to right, wavelength is decreasing. All right, so the wavelength is decreasing as we move from left to right. So what that also means is that frequency, if wavelength is decreasing, so you have a wave and the waves are getting closer, and so ultimately you have these waves that are really close together. My drawing's not the best on this, but if wavelength is decreasing, frequency, as we move from left to right, will increase. All right, so as wavelength decreases, frequency increases. So red light has a low frequency, and wavelength has a lower frequency, because we're looking at red light, which is right here. That's red. Red light has a low frequency and a longer wavelength. So we need to find one that matches that, and that should be D. All right, number 2, going to be the same concept, so I'm not going to go as much detail on this one. Which color frequency of light travels the fastest in a vacuum? So remember that these are all electromagnetic waves, and that all electromagnetic waves travel at the speed of light, 3.0 times 10 to the 8th meters per second. So that means E all have the same speed. Moving on, number 3. Which of the following forms of radiation has the shortest wavelength? So we already said that wavelength decreases as we move this way. So the shortest wavelength is going to be gamma. Moving on. All right. What happens to the energy of a photon if the wavelength is doubled? All right, so if we have a certain wavelength, and then so we have 4 waves right there. If we double the wavelength, what do we do to the energy? Energy is going to be reduced by half. All right, so energy and wavelength are inversely related, because remember that energy is equal to Planck's constant times the speed of light over wavelength. All right. Number 5, what is the energy of a photon with a frequency of 7.01? This number may be different on yours, but you should be able to see it. 7.01 times 10 to the 14, 1 over seconds, gives you Planck's constant. So as we look at this, we're going to use the formula E equals H C over frequency. No, over wavelength, sorry. And I'm going to pause right here, so I'm going to write out the question and then come. All right, so I'm glad I checked. The formula that we're using for this one is E equals Planck's constant times frequency. This is a frequency, and this is Planck's constant, so that's H. All right, so E equals 6.626 times 10 to the negative 34 joule seconds times 7.01 times 10 to the 14, 1 over seconds. Seconds cancel, so that means that our unit is going to be joules. And then as we're going through this, the answer 6.626 times 7.21 is going to give us 4.77. And then we have negative 34 and 14. When we do that, we add them together, so that's going to be times 10 to the negative 19. All right. Going through, and the other statement is that was actually number 6. This one is number 5. All right, so looking at number 5, it says determine the energy of a photon with a wavelength of 361 nanometers, and then it gives you Planck's constant and speed of light. Well, the first thing that we know is speed of light is measured in meters per second, so nanometers aren't going to help us. We need to convert to meters. So that's going to be our first step. All right, so again, first step is converting 361 nanometers into meters. 1 meter is equivalent to 10 to the 9th nanometers, or if you want to look at it another way, 1 nanometer is equivalent to 10 to the negative 9 meters. So when we do the math on this one, 361 nanometers, and that should be times, not equals. That cancels out nanometers. So 361 times 10 to the 9th, that's an exponent. 10 to the 9th equals, let me write that more clearly. Ten to the 9th will give us 3.61 times 10 to the negative 7 meters. Now, so we have a wavelength, we have Planck's constant, we have the speed of light. Remember that energy, one of our formulas for energy is Planck's constant times the speed of light over wavelength, because frequency equals c over wavelength. We can substitute this into that. Same formula, just a different setup. All right, so looking at this real quick, we have Planck's constant, which is 6.626 times 10 to the negative 4 joules seconds times 3.0 times 10 to the 8th meters per second. All right, so that means that we can cancel out seconds right here, and we're left with joules, meters, and then we have meters underneath there, and we can cancel that out. So that's going to leave our answer in just being joules. So now we just have to do the math. I recommend solving the top first and then divide by the meters, which would give us 5.51 times 10 times 10 to the negative 19. And again, your number here may be different, so just pay attention to that as you're doing these. All right, going through real quick on this one. True or false, two electrons can simultaneously occupy. True or false, two electrons can simultaneously occupy the same NL and ML orbital, and that is true. Of the following, which sublevel is filled last? We want to look for the highest energy level, all right? But remember that in the 5s, we have a 4d. So we're going to fill 5s first, then 4d. Because you fill 1s before you fill 2s, then you fill 2p, then 3s, 3p, 4s, 3d, 4p. So we fill s's before we fill p's, we fill d's before we fill p's, but remember that the d is always on the shell before. So the highest energy level that we have is 5s, but then we're going to fill 4d on that one. So the correct answer on that one is 4d. All right, continuing on, we are looking at question 9 now. It says the ground state electron configuration for aluminum is as follows. So aluminum is on the third period. It is in the first. It is in the first column of the P. So it's actually in column 3A. So what that tells me is that it has to end in a 3p1. All right, and if everything in front of that is filled, it's going to be 1s2, 2s2, 2p6, 3s2, and then 3p1, which is B. All right, which element has the electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d5. Now, notice right here that it says 4s1, 3d5. That means that the second electron in the s has been moved here. So another way of looking at this would be 4s2, 3d4, which your answer comes out to be chromium. All right. This has to do with a stability thing. If you remember, the d orbital has 5 orientations. So it's more stable to have 5 half-filled orbitals than it is to have the 4s, and let's just say that we had 2 in that one, and then in our D that we had an up and up and up and an up, with that blank, with this blank being completely empty. So this is a more preferred version. That's why it does that. You don't need to know that information so much as to know that chromium was our right answer. All right. Another way you could have done it is count total electrons, and it would have, if you would have just got the number of electrons by counting them. So I'll show you that you could have looked up that we have 2 plus 2 is 4, plus 6 is 10, 12, 18, 19, so that would be 24 when we add those 5, and then chromium has 24 electrons. All right. Which element has the following electron configuration? What is the following electron configuration of a neutral potassium atom? So number 11, remember that potassium is the first element in the 4th period. So we are looking for one that has a 4s1 as our final thing. This one says 4s2, and so E is the correct answer. It's 4s1. What is the correct electron configuration of potassium plus 1? So if it's potassium plus 1, that means it has lost an electron. So that means we're going to get rid of the 4s1, so it's going to be 3p6b. Moving right along. Number 13, in the Bohr model of hydrogen atom, the energy required to excite an electron from N2 to N3 is blank. The energy required to excite it from N3 to N4. All right, so remember that the distance between N2 to N3 is greater than the distance between N3 and N4. All right, so to move an electron from here to here takes more energy than to move the electron from here to here. So the energy to go from N2 to N3 is greater than the energy to go from N3 to N4. All right. When the electron configuration violates the Hund's rule. All right, so remember that Aufbau is you fill from low energy to high energy. So you fill N1 before you fill N2. Pauli talks about opposite spin. So that means you'll have an up arrow and a down arrow. Hun says that we fill all the ups, and if this was a P, we fill all the ups before we start filling the downs. All right, so we're trying to find which electron configuration violates Hund's rule. There's really no Y on that one, but the correct answer is D. 2s2, 2px2, 2py2. What you should have is 2px, 2py, 2 2py1 and 2pz1. Because when we're filling them, if we have 4 electrons to fill in the p, we would go up, 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 down. So that one violates Hund's rule because it's trying to say that we filled 4 electrons in that one. All right. Which of the following ions has the electron configuration of 2p6? We just need to find an electron that has either lost or gained 3 electrons to end up in the position of 2p6. All right, so when we're going through on this one, what we find is that nitrogen, when it gains 3 electrons, it shifts over to that particular noble gas. It will help to have a periodic table out for these, and so that you can see these. All right, which of the following electron configurations represents a transition metal? All right, for a transition metal, we're looking for something that ends in a d orbital. Transition metals end in a d. All right, so that's going to be D. And so that brings us to number 17. Which of the following represents the electron configuration of sulfur -1? So if we're adding 1 electron to sulfur, it's going to move from having 4 electrons in it to 5. So the correct answer is B, 3p5. So this is the normal configuration of it. When we add 1 more electron, it becomes 3p5. All right, which of the following is the electron configuration for Mn? Mn is a transition metal. It's in the 4th period. So Mn is going to be B, 4s2, 3d5. Again, if you have a periodic table handy, you can see that very easily. What is the noble gas configuration of calcium? Let me scroll down just a little bit. So this is just a standard calcium. Remember, calcium is in the 2nd column of the 4th period. So it is going to be noble gas configuration. Let me get out of this. What did I do? So the noble gas on the period above in the 3rd period is argon. So you're going to have argon. It's going to be one of these two. And it's in the 2nd column. So it's argon 4s2. Because that's what comes after because calcium is in the 2nd column. All right, moving on. Number 20. Which of the following pairs of electrons represents isoelectric species? So we need to find 2 that's going to have the same electron configuration. So we're going to do this for ions. So you can either have ions that look either isoelectric or ion in a noble gas that's isoelectric. You won't have standard configurations that would be isoelectric. All right, so looking at this one, number 20, is we have aluminum, and oxygen. Aluminum's on the 3rd period, oxygen's on the 2nd period. So if we gain 2 electrons in oxygen, it's going to go to that noble gas. If we lose 3 electrons in aluminum, it's going to go to the noble gas on the line above. All right, so they both look the same. All right, number 21. Which element has the ground state electron configuration of argon 4s2, 3d10, 4p5? All right, so we are looking for something in the fourth period, and in column 7, no, yeah, in column 7A. All right, so it's going to be a halogen, and the halogen that it'll be is bromine. And this is actually the only halogen. Another way to tell is this one is going to have, it has, in its valence shell, it has 2 electrons here and 5 electrons there, so it has 7 valence electrons. This is the only one with 7 valence electrons. All right, that one's a good one to know Lewis structures for, or Lewis dot diagram for. How many core electrons does an atom of beryllium contain? Core is inner electrons, so we need to look up the periodic table for beryllium, and you're going to remove its outer shell electrons. And so beryllium is in the second period. So it's going to have only 2 core electrons because N1 can only hold 2 electrons. All right, moving on. Number 23. A student draws an orbital diagram below for the 3p electrons in the s atom. What, if anything, is incorrect about the drawing? So we have, when we're looking at this, if we were drawing this one correctly, there's a couple of possibilities. You could have an up, an up, an up, and then there'd be a down on this one. The way this one is shown, you have a down, then an up, and then a down. A down, up, and a down. So if you were going to follow the pattern that you're showing the downs first, you should have had down, 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 up. You just have to have them opposite spin. It doesn't matter if it's an up or a down that comes first. You just have to be consistent with it. So B violates Hund's rule because we've started filling different energy levels. We didn't fill all in one direction first. All right, moving on. Number 24. Which of the following atoms has only 5 valence electrons? So we're looking for the one that has 5 outer shell electrons, which would be nitrogen, I believe, without looking at the periodic table. Yes, nitrogen. All right. Who developed the earliest form of the modern periodic table? This is one that you just have to kind of notice. Mendeleev and Moseley are the 2 big ones when it comes to periodic table. Mendeleev was first. Moseley improved on his design. All right. Number 27. Sorry, number 26. Aluminum loses its electrons. Loses its electrons when it forms an ion. How many electrons did it lose, and in which orbitals? All right, so it's going to lose 1 electron from 3p, and it's going to lose 2 electrons from 3s. All right, so 1 electron from the 3p, that's sort of correct, but not completely correct. 2 electrons from the 3s. So it's going to lose 3 electrons total. 1 from 3s, that's wrong. 3 electrons total, 1 from 3p, and 2 from 3s. So D is your correct answer. All right, which of the following metals would you expect to have the smallest atomic radius? All right, remember atomic radius. If this is our general periodic table, and I know it's not great, but remember radius is larger as we go in this direction. So the smallest element on the periodic table is going to be helium, and the largest would be francium. So looking at this, we need to compare where they're located. So which one would be expected to have the smallest of the choices that we have? Ta, tantalum is the smallest based off of that rule. All right, 28. Rank the following atoms in order of decreasing ionization energy. So again, if this is my periodic table, ionization energy decreases as we move this way. So this is low, this is high. So lithium, beryllium, barium, and fluorine. Fluorine, so this is basically going across the period. So fluorine is going to have the highest. So that means it's going to come first. Lithium, since it's in column 1, is going to have the lowest. Lithium has to be last. And then beryllium and barium have to be in between. So looking at that one, number 28. It's going to go fluorine, beryllium, lithium, and barium. Sorry, barium is on a period lower. So fluorine, beryllium, lithium, barium. All right. Rank the following atoms in order of decreasing size, largest to smallest. So again, remember that size is large here, small here, so it increases, and actually this one increases in that direction. So it increases as we move down and to the left. So in this one, we just need to look it up on the periodic table, put them in order. The correct answer should be A. Fluorine is going to be the smallest, then nitrogen, then boron, then magnesium, then rubidium is going to be the largest. All right, which of the following atomic radii comparisons are correct? All right, so when we're comparing ions, remember that if it's a negative ion, so an anion gets larger. Because we're adding electrons and it creates a wobble. Cations get smaller. So what we're looking for is either a cation where you have saying something that the cation is less than the normal state, or we're looking for an anion saying it's greater than. So D is the correct answer. Se negative 2 is greater than Se. Sorry, that's a 2 plus. Bromine -1 is less than Br. It's incorrect. Sorry, I was looking for the one that was incorrect. So that one's correct, that one's correct, that one's correct, and that one's correct. I misread the question, so we're looking for the one that's incorrect. All right. So to do this one correctly, the sign should be bromine is greater than Br. All right. Number 31, which property decreases as you move down the column in the periodic table? So I'm just going to do these. Radius increases, electronegativity decreases, ionization energy decreases, metallic character increases. So of the choices that we have, atomic size, which is radius, it increases. Ionization energy decreases. All right, and then in which direction in which direction on the periodic table does metallic character increase? So it increases as we're going down, and it increases as we're moving left. So ionization, metallic character So the further you are to the left and the lower you are on the periodic table. So it increases as we go down and to the left. B. So that's number 32. And then the last question, number 33. Which of the following series of isoelectronic ions correctly list the ions in order of increasing size, smallest to largest? So again, this one is going to be helpful to have a periodic table. All right, so looking at this one again, which of the following series of isoelectronic ions correctly listed in order of increasing size, smallest to largest? So remember, so the atoms that we're dealing with here, we have calcium, we have potassium, we have chlorine, and we have phosphorus. So phosphorus, and just to kind of mark them, I want to mark them on here. So we have phosphorus, we have chlorine, we have calcium, and we have potassium. So phosphorus becomes a -3, so that means phosphorus goes here to argon. Chlorine becomes a -1, so that means chlorine goes here to argon. And then calcium loses 2 electrons, becomes a +2, so it's going to come to argon. And then potassium is going to lose 1 and become K+, and comes to argon. So they all look the same. So the largest is going to be phosphorus, because it gains 3 electrons. So phosphorus is greater than chlorine, which gains 1 electron, and then it's going to be greater than potassium, because potassium loses 1 electron, which is greater than calcium, which I just happened to put them in the right order because calcium is going to be the smallest because it loses 2 electrons. So it lost the most, so that means it's going to have the tightest pull on the nuclear because the nucleus is going to have the greatest charge. All right, so the correct answer is A. It just so happened I put them in the right order to begin with. All right, so that is it. That concludes the review of homework 9.